All right, good morning. Welcome to Wednesday of week 3. There was no Monday for those of you following along at home. This here is perhaps an example of someone with way too much free time. So this, I think, is the entirety of the original Star Wars movie presented essentially as animated ASCII art. So if you look at the hacker edition of Problem Set 1, we offered this URL as just this crazy degree to which people can take ASCII art, but it's nonetheless kind of neat, at least to watch for a couple of moments. So do feel free to pull that up. I'll link it on the course's website. A few announcements. So one, because of Drew Faust's inauguration this Friday, we've been relocated from this room over to Emerson, which if you go out the back door, take a right, that's Emerson, right next door. So we're in Emerson 105 this Friday only, so do bear that in mind. We'll post a sign on the door here in case you show up here by accident, though you might not even be able to get into the building, I'm not sure. Quiz 0 is next Wednesday. So this first quiz is just meant to be another angle by which we can assess just how well you're absorbing the material. And for you, it's an opportunity to make sure that you're keeping up with the course and generally understanding the concept. So do read over one of today's handouts at your leisure. Take particular note of one logistics. So that you guys have enough room to spread out and we can have every other seat, the school has given us 3 different lecture halls to assign you to. So we've gone ahead and used the first letter of your last name to decide where you're headed. Some of you are here, some of you are in Emerson 105, and some of you are in, if you've ever been, the Fogg Art Museum, which is literally right across the street. So we'll have teaching fellows directing you lest you've never been to these places, but do feel free just to ask a question or look up the rooms online. So that's Wednesday of next week in lieu of lecture, same time, same place. And do take note that we'll be using the coming week sections, Sunday, Monday, Tuesday, as review opportunities. And this Friday, will we post prematurely on the course's website under sections the week section notes, which will contain a bit of review and some sample questions. As I note in this handout, we're not releasing previous year's exams as practice exams because they're simply too different from the approach we've taken to the curriculum this semester. I think they would only mislead, if not scare. This, out of order, no problem set due next Friday so that you can focus on this quiz and then finally have a bit of a respite after these past few weeks. And then this, don't drop. So the drop date is coming up. And please, I would invite you, especially those of you who we keep calling less comfortable, if you're entertaining the idea of dropping because you've had trouble keeping up, if you feel you're in over your head, if you've been a bit scared by all the chatter on the bulletin board by those more comfortable, at least engage myself, the head TFs, your TF, in a conversation so that we can at least either assuage your concerns or at least confirm that this is what you should expect, depending on your circumstances. So at least give us that opportunity to win you back. Any questions before we forge ahead? All right, well, now begins the first annual Looking Up a Phone Number contest in Computer Science 50, for which I need 2 volunteers to come up front here to receive these 2 phone books and execute a couple of algorithms for us. See, I knew this would be hard. So to sweeten the deal, it turns out that these phone books come with your chance to win $2 million with these little scratch-off. Okay, here we go. Weena, come on up. One more, come on down. All right, so these are yours to keep. I will need your signatures ultimately, too. So that's the cost so that we can have you here on film. And the task here is as follows. What's your name?
Nathan.
Nathan, okay, you can sign that after. That's fine. So we have Nathan and Weena here. Each of them has a phone book. And needless to say, we're going to execute one of those algorithms we saw in week 0. So Weena, I'm going to fix this contest, unfortunately. You're bound to lose because we're going to ask that you execute the so-called linear search algorithm, which recall was this page-by-page approach to looking up a phone number. And you, by contrast, are going to get the fancier algorithm, the so-called binary search, or divide and conquer. And if you recall from the first day, that was my dramatic throwing half of the phone book on the floor constantly. So this is a legit Verizon phone book. I'm going to ask these guys to look up, let's say, a topic like plumbing. So on the count of 3, I would like each of you, executing your respective algorithms, to find us a plumber. Go. Okay, better hurry up, Weena. We'll take it. A round of applause if we could. All right. So congratulations. Please walk away with your potential prizes there and just leave that for me at the end if you don't mind. Okay, so here's where we were. So I think Weena got maybe, we'll assume she was in the yellow pages, so maybe to this point. And then here we had, with our divide and conquer strategy, a much smaller problem. And this was precisely the point. And perhaps if you continue on in computer science, please don't, next time some instructor asks you about binary search, start tearing things apart. Because that's not an inherent part of the algorithm, but it captures, hopefully, the spirit of really shrinking this problem again and again and again into something that's quite more manageable. And just to talk in terms of order of magnitude, let's say that this phone book had 1,000 pages, or for the astute, 1,024 pages. I mean, how many times would we have had to, with divide and conquer, look to a page in that phone book to find, say, a plumber? Maximally. So just 10, right? Because how many times can you divide 1,024 in half, in half, in half, in half? Well, you can only do that about 10 times, and assuming you end up then right at the page you're looking for. By contrast, if this phone book had just 1,000 pages and we did this so-called linear approach, this is 1,000 steps maximally. P for plumbing certainly isn't in the beginning of the phone book. It's roughly in the middle, but even that's 500 lookups as opposed to the 10. So it's the spirit of this algorithm that will motivate some of our discussion today, which is trying to put words, trying to put ideas behind this notion that the design of your algorithms can ultimately very much influence how much time you as the developer are going to take writing these things and how much you, the user, are going to take running these things. So I'm not going to force all of you to stand up and meet each other again, but also recall this algorithm from week 0. So the goal of this algorithm, in which all of you stood up that day, executed this thing, was to count yourselves. And this was in contrast to my more naive approach of 1, 2, 3, 4, and so forth. Another so-called linear algorithm, as though I'm just walking a line, pointing at everyone one at a time. Well, this was similarly sort of a divide and conquer. There's certainly a similar spirit, because what was happening on each iteration of your execution of this algorithm? Just visually, what was going on in the room, besides a great mass of confusion? All right, so half of you were sitting down. Half of you were sitting down. So the question ultimately boils down to the same. How many times can we get away with having half of the class sit down again and again? And that, too, gave us what we'll see today is what's called logarithmic growth in the running time of an algorithm, because you're dividing something again and again. And just to make this more real, here's a little sneak preview of what it means to, say, be something that's linear or something that's logarithmic. And let's actually not just use this, but let me go ahead and pull up Excel. I'm going to use the little chart wizard here as an interactive demo. This isn't exactly what Excel is meant to be used for. But let's suppose that we want to quantify the problem as follows. So n, henceforth, is going to be the variable we use verbally to describe the size of some problem, the number of students in the room, the number of pages in a book. So I'm just going to fill this with some initial values, like 1, and maybe 20, 40, 60, 80, 100, 120, and so forth. Now suppose that my running time of my algorithm is just linear. It's that naive approach of me just pointing at each and every one of you. Well, here I'm going to use a formula. So now my running time, we'll call it T of n, just to be a bit formal today. It's just going to be n. So in Excel terms, this means it's just going to equal whatever n is. So I'm going to copy this, paste this in, and we're going to see a whole bunch of duplicate values. But let's do a comparison now. I mean, what would be slightly more clever than my just counting you one at a time ad nauseum? All right, so counting by 2s, right? I mean, this is a useful childhood heuristic. 2, 4, 6, 8, 10, 12. So in effect, I've doubled I've doubled the speed of my algorithm with a simple change. So let's capture that. So the running time, T of n, this time is just going to be n over 2, because I've literally sped my thing up by a factor of 2. So in Excel, and this kind of details you don't have to worry about if you've never used Excel, it's just 2 divided by 2. Let's copy paste that. And as you'd expect, we now have running times that are half as long. But now let's take it one step better and suppose that we had you guys execute this algorithm. And granted, we're cheating a bit with having you execute this algorithm, because conceptually, what's different about me counting and, say, you counting? And the title's a bit leading as well. Right, so we're assuming that you are essentially individual CPUs. Essentially, I'm throwing hardware at the problem, so to speak, as opposed to better design in the case where I'm just counting in 2s and 4s and 6s and so forth. So I'm still just one CPU. You presumably are 200 or 300 CPUs, so just intuitively you would expect to have a speed up. But even so, it's something we can capture here. So let's suppose now that our running time, t of n, is what we'll describe as log, base 2 of, rather, n. And the base, turns out, doesn't matter so much. But if you vaguely remember logarithms, it's graphs that look like this. They kind of curve upwards and gradually go to infinity, typically. So here we're going to have a equals log of a2 and base 2. And the base here just means we're dividing in half, in half, in half. Let's save that, copy this. All right, so now I have a little chart. And you can already see the spoiler here, just numerically. And I know this font's a bit small, but notice that if your algorithm is running in logarithmic time, clearly the number of steps involved is fewer. But let's see if we can visualize this. So let's highlight this, use the little chart wizard, little XY scatter plot. We'll connect the dots. Next, we'll choose all these defaults, defaults, defaults. And now I have a nice little chart. Okay, also a bit small to see, but notice that the top line there is n, series 1. The pink line there is series 2. And visually, it's about half as bad as the original one. And then notice the yellow is significantly better. And if we plug in even greater values, this trend is going to continue such that if I go on up from, say, to 140, 160, 180, 200, 220, and let's see how Excel likes this. 500. So just notice that the difference between these algorithms becomes even more and more striking as time goes on. And if we change the scale, you would feel that, for instance, let's see, when our input, n, there are, say, 300 students, or actually, let's take the 500. Actually, let's go one step further, 1024. So when we have 1,024 pages or 1,024 students, the running time of, say, that counting algorithm or that search algorithm, it looks like, it barely takes what? It's 10 steps, 10 iterations. Meanwhile, if we did anything linear or even something marginally better like n over 2, we're literally talking about 1,000 steps. And this trend certainly continues, and it only gets worse out toward infinity. And the interesting thing with computer science these days is that n, so to speak, is getting increasingly large. The number of users on Facebook and the number of friends you have on Facebook, the number of web pages that Google indexes, these are instances of large n, where implementing intelligent, clever algorithms really pays off. I mean, Facebook, to their credit, has done a really good job at making a website that is fast. It's responsive. You don't typically sit there waiting for pages to come up, even as it's checking all of your current friends' status updates and the like. Google, too. I mean, my God, you click submit, and it searches the web, so to speak, practically instantaneously. These are not algorithms that are, say, linear in their design, or even n over 2. They're typically much better. So what we'll begin to look at today is precisely this question of design. And that's actually a good segue to this final announcement here. So problem set 0, recall, was on Scratch, which was really meant to be a fun introduction to the course's material. But clearly in problem set 1 and now in 2, you're focusing more on formal programming in C and such. We'll know that when it comes time to evaluate your programs, the axes along which we will typically evaluate them, that is grade them, are simply these 3. So we will typically take into account for a given program the correctness of your program, that is, how well does it satisfy the explicit requirements in our specifications. So does it do what it's supposed to do? Design. Just how well written is your code? How intelligent is your design? And with problem set 1, we were much more concerned with correctness than anything, especially since for most of you, this was the first thing that you actually programmed in a language like C, and that's fine. And as we proceed with problem sets, we'll begin to emphasize these 2, which I'll get to in a moment, increasingly more once we've actually said something about design, like today, and said something about style, which we will next week. But design really captures the spirit of just how readable the program is. If I, say, as an experienced programmer, can look at your program top to bottom and understand how it works. And this isn't so much to make fun, but to make clear where you'll eventually be. I mean, when I've myself done a few hours of office hours in the Science Center and online, there have been some of you who, for instance, with the nested squares problem and BMI last week, like the stuff worked. And it was computing people's weight. And it was printing out the square. I have no idea how some of your programs were actually working. I mean, you sit down at the terminal. We, as TFs and instructors, are looking over your shoulder thinking, my God, I mean, it's scary to us to even help you debug these things sometimes because, I mean, as some of you might have been inclined to do, sometimes it takes a bit of tinkering with your code and eventually it works. But even you, dare say, aren't quite sure how it works. Well, when we get to focusing more on design, it will be hopefully clear to both you and both us exactly how these programs work. And I think you, too, will have a revelation come semester's end if you look back at your problem sets 1 and 2 and probably 3 and are just embarrassed, perhaps, about how you implemented some of those programs. But again, that's to be expected, because that's why you're here. Finally, style. This is something that one largely learns by practice and by experience and by exposure to TFs and my own examples in class. By style, we mean things that are purely aesthetic. How well are you commenting your code? How nicely are you indenting your code? Some of you not very well from what I've seen. How well are you using parentheses appropriately? And just aesthetics that functionally don't change the program and intellectually don't change how the program operates, but visually and to another programmer who needs to either grade or in the real world actually use or modify and update your code. That's where style comes in. And this is something we'll focus a bit more on next week when we start, for instance, laying down certain heuristics that are useful to follow. But even style is more of a religion than any of these other things. And you'll see the TFs doing different things in section than I do here in lecture, commenting styles, what we name variables and such. But it's ultimately a matter of personal preference, which hopefully you too will adopt before long. All right, so any questions about the axes along which your problem sets will be graded? No? All right, so let's forge ahead. So here is, just to make more real, the mock-up I just did in Excel, what the implications are when n starts to get really big, when we start to measure the performance of our algorithms in this very general sort of back of the envelope approach. So this is just a big table of numbers. There's really nothing magical about this. You can compute this all with a calculator. Look at this third column here where there's n, and just take note that, for instance, if n, the number of students in the room, is only 64, and we use an algorithm that is linear, obviously it's going to take 64 steps to count those students. But by contrast, if you look at the second column next to 64, well, all that's telling you is that if you have 64 students in the room, how many steps is it going to take for, say, they to count themselves using the more intelligent parallel processing approach? Well, only 6, because that's how many times you can have 64 again and again and again. But the interesting takeaway is actually in the other direction. Starting this week, today and Friday, we're going to look at algorithms that aren't just linear. And they're not even logarithmic, but they're exponential. And they are quadratic. They're polynomial. That is, they're worse. They're slower, but usually out of necessity because of the types of problems we're solving. But notice the difference. If we at some point this week encounter an algorithm that's in this n squared column here, and for instance, the size of the problem we're trying to solve is roughly 1 million, as indicated in the n column here. Notice the difference between an algorithm that runs in so-called quadratic time, n squared, and we'll see examples of this on Friday, versus something that is marginally better. And marginally better will soon be for us n times log n. And we'll see exactly how you can implement algorithms that are faster and can be modeled in terms of their performance with these kinds of equations. And this isn't really a mathy course, and we're not going to start solving equations or anything. Ultimately, these are meant to be sort of back-of-the-envelope calculations that just give you a sense of how good your algorithm is or how bad it is. But more poignantly, we'll feel on Friday when we do some demonstrations of sorting algorithms just what it feels like to implement something that's n squared versus, say, just n or n log n. So here's the notation that we're going to start using henceforth. When we want to talk about just how good an algorithm is, or really just simply what its running time is, what its performance is like, we're going to use these broad terms, one of which is just called big O. So if I say that some algorithm or some program you've written is in big O of n, what? And that's where we're at. All right. If I say that an algorithm is in big O of n, that's just the more formal way of saying that the algorithm is linear. And just quick sanity check, what's a linear algorithm? A big O of n algorithm we've seen thus far? And what's that? So go straight through the phone book from first page to last page, or my counting algorithm. So big O, though, specifically means an upper bound. So in other words, when Weena was executing her linear search algorithm of that large phone book from first page to last page, that was in big O of n, so to speak, that algorithm, that program that she was executing. That means that in the worst case, if I didn't ask for a plumber, but a zoo in the local area, she might have had to look at all n pages in the phone book. So in that sense, big O of n means the algorithm, in the worst possible case, the worst possible input or question you ask of it, could take as many as n steps. So the counterpart to this is that there are also ways of expressing the lower bound of an algorithm. So if you say that something is in omega of, say, n, that means in the best case, it's going to take n steps as well. All right, so best case, n steps as well. So it's a lower bound. So with that said, in the general algorithm that Weena was executing, forget about what I asked her, because I asked her specifically about a plumber, but generally speaking, the algorithm she was executing with the phone book there, first page to last page, what would you say is the best case running time, the lower bound on the running time of that algorithm? So it is, in fact, just 1. So even though we've been talking in terms of variables, you can certainly imagine a situation where I ask for, find me a local animal hospital, which might very well be on the first page of the phone book because it starts with A, and therefore it might be on page 1. So quite literally, we might have executed an algorithm in just 1 step. Maybe 2 steps, maybe 3 steps, but the point is it might be some very small number of steps. And we would typically quantify that by saying omega of 1. But that same algorithm of Weena's, in the worst case, what was it? Just to reinforce, what was this? So an algorithm then can be described often in 2 ways, the best case running time and the worst case running time. And notice I'm not even getting into the minutia of exactly how many steps were involved with actually physically turning a page and moving to the next one. I'm sort of taking an aggregate view and saying the act of flipping a page is an operation. Similarly, when you all counted yourselves in week 0, yeah, there were like 6 steps on the board, but conceptually it was like you were doing one thing again and again and again. So in that sense, what was the running time of your algorithm, say in big O notation? In the worst case, how many steps did your self-counting algorithm take for the class as a whole? So it was log n, right? That was the lesson we came away with. It can't sometimes take just 1 step, right? Unless one of you happened to just know the answer and shouted it out in the first step. Realistically, you have to execute the full algorithm. So sometimes it's sort of meaningless to talk in terms of worst case and best case because it's always the same case. And we have a way, and this is a bit of an abuse of the term, but there's a way you can also express that, though it's a more formal definition than I'm using here. If it turns out that your algorithm is in both omega of something and also in big O of something, it is safe to say that it's in theta of that same value, which means it's a coincidence of both the upper bound and the lower bound. So that's all it means. And sometimes it's inapplicable because if these 2 values are different, they're not the same. There's not a coincidence of these same bounds, so you don't speak in terms of theta. Okay? So that's it. We'll continue to use throughout our look at algorithms this kind of notation. But intuitively, what's better, an algorithm that's in big O of n or big O of log n? So in general, hopefully it is in fact big O of log n that's better because that means in the worst case, it's only going to take logarithmically many steps as opposed to a whole entire n steps. But even that's not necessarily the case because we're talking in general terms. You can certainly come up with situations, as we will, that violate even that expectation. So here's the formality, which I won't dwell on. But for those of you who are mathematically inclined and would like to more formally define each of these terms, that would be the formal notation. But for us, the intuition suffices. And we will, in fact, often just speak in terms of English, especially in terms of big O. Typically, a computer scientist, an engineer will speak in terms of big O, even though it's kind of a loose upper bound on what they're talking about. But it's often easier to talk in terms of English. So if something has a constant running time, well, you might, that is big O of 1, you would call it constant, logarithmic, linear, supralinear, quadratic. You'll begin to hear these terms uttered by myself and the TFs. It just means big O of something or other. And we'll see this in more concrete terms soon. All right, so now we move on to a problem where we can begin to apply this logic. I would love to have one more volunteer. No $2 million. Oh, did either of you win anything? Not yet? You don't know? OK. All right. We should talk after if so. All right. So I need one more volunteer. Yeah? No? Come now. This is non-speaking role. Anyone? Okay, come on down. What's your name? Merritt. Okay, come on down. And let's go ahead and head on over here. And we have what are essentially now 2 arrays of integers on the board. All right, so this is sort of like Price is Right now. So we have 8 values behind closed doors here, so to speak. So it's like an array of ints of size 8, to use last week's nomenclature. What I would like you to do, looking at the top row only, treating it as an array, is find for us the value 17, which I have hidden behind one of these doors. Do whatever you need to do to make that happen. Find us the value 17. Yep. Well. Okay. No, that was a 0. And holding them up high just so folks can see what's going on. No. No. Okay, so she found it. Okay, so sure, a round of applause, because I'm sure that was a little awkward. Okay, thank you. We'll keep you up here for one more exercise in a moment, but let's see now how the audience would describe, if I could, your algorithm. So you solved the problem. How did she solve it? And then we'll let you answer the question. How did she solve it? Yeah? Okay, so pick any window that I haven't already looked at and open it up. And would you agree, disagree? Yeah. All right, so what was the pattern there that you were following?
Random.
Okay, random. All right, so that's fair enough. And we will get to the point you started in the middle, you jumped around, you went over here. You didn't even look, I think, at this one, and then you came back over here, and that's fine. So we will actually empower you at some point with a function called rand that lets you, programmers, generate random numbers. And arguably, that's a correct approach. But it wasn't quite random, right? Because I didn't notice you ever do what, if I can ask a leading question here. You never repeated. So clearly you were remembering, or maybe you were just lucky you weren't looking at the same piece of paper multiple times. But that's a design consideration to take into account when you're actually writing a program, lest the thing, by bad luck, gets stuck in effectively an infinite loop, at least probabilistically. All right, so worst case running time of your algorithm using this so-called asymptotic notation of n and big O and such. What was it? Okay. So okay, good. So it was 8 steps worst case, and let's just generalize that. So there are n doors now in the general problem. So it's big O of n. So the algorithm, random in this case, was big O of n. What would be a refinement if you were to do that again? And I'm sorry, this actually became very much a speaking role. What would be the next improvement on this algorithm, would you say? I mean, random worked well for you, sort of. It still took you 6 steps. What else might you have tried? In other words, can you come up with a different algorithm than the one you used, or is that it?
Like looked at more?
Okay, so fair enough. So we could take the same approach of my counting in 2s, and you certainly could have looked, say, at 2 doors at once, and that would effectively double the running time of your algorithm. So in terms of big O, though, what would that algorithm be? So n doors. Yeah, so in effect, the algorithm then becomes one of n divided by 2. But here's the catch, and I'll get you out of your misery here in a second. So here's the catch. In general, when we talk in terms of big O and omega and theta, we throw away any kinds of constant factors like 2s. Because what we don't want to get into the habit of doing is saying that this algorithm runs in big O of n. And then I can just say, well, why don't you take that algorithm, run it on my dual-core Pentium computer that's twice as fast. Now the running time becomes n over 2. But it hasn't, right? Nothing materially has changed about your algorithm. And so to give us this independence of the hardware we're actually executing algorithms on, or the speed of the human executing them, we'll typically throw away those numbers. So the takeaway for now is that even if you did take this clever heuristic, like I might have done with counting, of opening 2 doors at once, fundamentally, it's the same running time. And we would say that that approach of opening 2 doors at once is also in big O of n. And intuitively, what this means is that if we're talking about 1 million doors, 1 billion doors, there's not a huge difference once you really get out toward infinity between, say, 1 billion and, say, 500 million, or even worse. I mean, in real terms, there might be. But when you start to look at graphs and start comparing things like we were with Excel, just consider just how low the yellow line gets at that point and how big the blue line gets. It doesn't really matter if we quibble over whether something's blue or pink, that is n or n over 2. All right, so I'm going to put you, you can opt out now, or you can go for the grand prize of searching the bottom row once I give you some more information. So would you like to return to the audience, or would you like to go one step further?
Try again.
Okay, I wish I had actually thought to bring a prize, because I don't have anything. So, but the suspense is nonetheless tense. So how can we do better? Well, we've seen improvements in the past on algorithms that we've executed, for instance, with the phone book. What was the approach that was fundamentally different about the phone book that we used divide and conquer for? Yeah. Yeah, so that's the thing. You both had the advantage, or at least the assumption, that your phone books were ordered. So I've not given Merritt any sort of assumptions. In fact, the numbers behind these doors are in fact random. So frankly, there is no way that fundamentally you could have done better than just guessing randomly or linear search from the left over here or the right over here. Because the things are randomly assigned, it might have been perfect, you might have found it the first time, or you might have gotten stuck looking at all 8. But here's an assumption and I'll give you. I have taken the time before class to very carefully sort all 8 of those same numbers. So the goal, again, is to find 17 in this bottom row, but you may now leverage the assumption, if you're inclined to do so, that the numbers are sorted. What would you do? Find us 17. This is perhaps the worst volunteer role we've had yet. Okay. Oh, OK. OK, good. So a round of applause. This is difficult. And last question then. Same question, though. What was your algorithm there?
In terms of...
So describe what you did. Was that still randomness?
No.
OK, what did you do?
Look towards the end to see if it was from the upper end of the numbers or the lower end.
OK.
And then from there, assumed where 17 might be placed.
OK, good. So I didn't tell you if it was sorted from smallest to largest or largest to smallest. So that was quite reasonable. You found a low number here. So the assumption was then that you could jump further ahead. And I'll take you out of your misery here. And I do have a nice legal form for you, if nothing else, if you want to return that to me afterward. And now let's push a little harder now on this assumption, because Merritt did a perfect job, I think, of illustrating for us, perhaps accidentally, that randomness, 1, is a perfectly acceptable approach for an algorithm. But 2, we have this possible refinement of just doubling the number of things we do at once by, say, throwing 2 CPUs, or in her case, 2 hands at the problem. But even that, we're going to say for now, doesn't fundamentally improve our algorithm. But if I pre-sort these values for you, we can go from an algorithm that's in big O of n to what in terms of big O? So log n. So the concept is actually identical to what we did with the phone book. And in fact, I would tweak the algorithm you took here, which was very reasonable. You again use these heuristics. But I would say in general, the safer approach, if you do know that they're sorted and you know further that it's from smallest to largest, where should we start looking? So right in the middle, just as you did with the phone book. So here we have an even number, so we have to do a bit of rounding if we actually wanted to code this up. But I'm just going to assume that it's here. So I'm going to break the tie arbitrarily. OK, 23. Well, just like the phone book, what do I now know is the case? It's over here. The 17 I'm looking for is obviously over here. So conceptually, it's as though I've thrown away this half of the problem. So now I know that 17 is somewhere in here. Where do I go? Well, no, I did this time. I said from smallest to largest. Yep, so from smallest to largest. So if, assuming you do know that, you go to the left. So I know it's within these 4. What do I look at next? So in the middle, and again, we have this rounding issue, which we can deal with in code. All right, so let's go here. All right, so 7. So it's smaller than the value I'm looking for. So where do I want to look to next? Well, it turns out there's only one value that remains, because effectively we've said it's not that direction and it's not that direction, which means hopefully it's here. And in this case, it is. And if not, the takeaway is still the same. Even if that were 18 and thus the number is not there, what's the worst case running time of the algorithm? It's still log n, right? Your answer is just different. It's not there. So just because the value is not there doesn't mean that now I have to go back and double check, damn, where did that number go? Because if our assumption was that the thing is sorted in the first place, if you don't find it using this accurate divide and conquer strategy, it's just not there. It's not there to be found. So this is an example of 1, linear search, and ultimately binary search. So let's formalize this a bit but not so much in C today. In fact, you'll see, those of you itching for a respite from C itself, we only have 5 coding examples that we'll actually do this week in C source code. More of it will be concepts. So here's what's called pseudocode. And we've seen this in weeks past. Pseudocode is this amalgam of English and programming syntax. There's no one flavor of pseudocode. The point of pseudocode is just to get across the idea to someone without getting hung up on semicolons, parentheses, and the like. So here is an algorithm for searching behind doors, or arrays in this case, that finds a value if it's there, and if it's not, it just returns false. It's not there. So what's the algorithm really? Well, in pseudocode, I might say for each element I, and the implication or the assumption is you start from left to right or right to left. It doesn't really matter. It's the same. And I'm going to check if I, the current value I'm looking at, is equal to n, the thing I'm looking for, return true. I found it. Otherwise, move on, move on, move on. So that would be, if Merritt, I had asked you to actually write out pseudocode for not your random algorithm, but one in which we started from left to right or right to left, we might put up something like this. So the big O running time of this algorithm then, to be clear, was what? So it was n, but now you can see it more. Conceptually, it might have been clear. But now if you actually look at the code, be it in C or pseudocode, what is it about this program that makes it linear, that makes it big O of n, in terms of programmatic constructs that we've discussed? Yeah? Exactly. That it tests every value. Specifically, the construct that's inherent in there, even though it's sort of hidden with pseudocode, is a loop. And typically, a loop will iterate some number of times, in this case, for every element, for each element, which is n in the general case. And so there's our big O notation in code. Well, what about binary search? So it's easy to talk about binary search, but it's a little ugly to actually look at the code. But here is one approach to defining binary search, as was the example for our second row of doors here, in a way that we could actually translate to C. And I won't dwell on those rounding issues. You can, in fact, fix them by using floor or ceiling or integer truncation when you divide a number by 2. Suffice it to say, you can deal with that problem depending on how many doors there are or elements in your array. But let's just take a look at the spirit of this thing in code. Essentially, the idea of this starts with this inside of this loop. Let middle, some variable, equal first plus last divided by 2. And it turns out that mathematically, that just means that we don't have to assume this is the 0th element and this is the 7th element. Rather, we can do this in a general sense, so long as we know what number each of these cells is. And this allows us to reuse the same code. So the middle is just the sum of those divided by 2, which is going to put us right here. And those two conditions, if I is less than the value in the array in the middle location, then update last and repeat. Otherwise, if it's greater than that, move to the right. Otherwise, return true. You found it. And again, I'm going to go over this quickly just so that we don't get hung up in the details. But just for now, take this away as just a more formal write-up of what I think is much more clear just intuitively. Divide in 2, go left, go right, repeat. That's really the interesting takeaway for today's purposes. This then might be called iterative pseudocode. But we can use this same example to introduce this new programmatic concept. Not so much syntax, because you really have all the syntax you need for now, but this idea of recursion, if you've never heard it before. It turns out that in many programming languages, C among them, a function can call itself. And this is kind of a neat thing, and it might actually worry you at first, because what might be the immediate danger of a function calling itself? Right, this infinite loop. That seems kind of silly. If the thing calls itself, well, how is it ever going to break out of the cycle? Well, it can do so by being written in a way that you special case at least one of your answers so that you break out of this otherwise infinite loop. So here's a program that computes, and again, not to dwell on math, but just because it's nice and simple to do, the sigma function, where you take all the values, say, from I, where I is 0, all the way up to n. In layman's terms, if I give you n, give me all the numbers of n plus n minus 1 plus n minus 2 all the way down to 0, and give me back the answer. So sum up all the numbers between 1 and n, 0 and n equivalently. So how might we actually do this? Well, let's actually take this a bit slower in code. Let me pop over here. So nano, we'll call this 1.c. All right, so I have int main, and I'm not going to bother so much with comments now. Do I want to do? Let's see if we introduce this for reference. Yep, I'll go ahead and use our library. So int argc char star argv. All right, the first thing I want to do is go ahead and allocate an answer variable, because that's what I'm going to use to put our answer, and a value n, which I'm going to ask the user for. So I'm going to go ahead and make a shorter version of what you have a printout of for today's purposes for reference. And I'm just going to say n gets gent int. And I'm going to assume the user is not going to try to mess around with me, and he'll actually give me an int, and we don't have to sit there in a loop. And now once I do this, what I want to do is punt. I want to have a function that I or someone else will write actually give me back the answer. So I'm going to call this the sigma function, but I could call it foo for all I care. Pass it n, because I want to get back the value of all the numbers between 1 and n. And then all I want to do is print out. So printf, what do I want here to print out answer? Yeah, so just a D, new line to make it pretty, followed by answer. So that's a program, but I've obviously assumed that someone's going to get around to writing sigma. So let's do that. So down below, I'm going to go ahead and write sigma. What should the return type be of a function that adds all the numbers from 1 to n and returns the result? All right, so int, that's easy, called sigma. What does it take as a parameter? OK, so it's going to take an int too. Does it matter what I call it? No, I could call it n just because that tends to be the default variable name for numbers that a programmer will use. But it's just a coincidence that it's also called n. Is this problematic that main and sigma might have the same variable names? No, it's different scope, right? And that we looked at last time. But if we want to be ever so clear, we'll call it m. All right, now what do I want to do? Well, if I want to sum up all of the values between 1 and m, well, that sort of suggests that I want to just do a loop. So I'm going to do a quick sanity check, though, because if this thing is really a bad number, like less than 1, I don't want this thing to end up itself in an infinite loop. So if that happens, I'm just going to, by default, return 0 and just say this is not possible. Can't do this. Not going to try. But otherwise, what I'm going to do is what? I want to iterate from 1 to n and sum up all these values. So OK, so I actually am going to have an iterative variable, so int I. And why don't I go ahead and make a variable sum? Now, what do I want to do? For maybe I gets 0, or that's silly, right? Why bother adding 0 in? 1. So I is less than or equal to, excellent, m. And then I++, so some typical syntax. And now what do I want to do? Yeah, so sum plus equals I. That's all, right? So that loop will run m times, and it will add each time the ith value to the variable sum. What do I ultimately want to do with that value? So I want to return, presumably, the sum. OK? What's a bug in here? What's a danger I've run? Right, so it's fine if I didn't initialize I up here, because I do eventually initialize it later. But sum could have, as some of you have seen, given certain bulletin board discussions, what value in it? I mean, who knows? It could have anything in it. It could just have garbage data that's been left over from some previous execution of something. So let's initialize that to 0. So assuming I didn't make any syntax errors, there is one remaining problem here. So one, I do need to include this header file, so I can use printf. I also need to include CS50's header file so that I can use getInt. And I need to do one other thing. Otherwise, the compiler is going to yell at me. Yeah, so I need that prototype of the function. Stupid, but I need to tell GCC what function to expect, what it looks like. And it looks like an int return value. It's called sigma, and it takes int as a parameter. And it turns out with prototypes, you don't need to name the variables. The compiler doesn't care at that point. It just wants to know what types of variables, what types of arguments to expect. All right, so if I didn't make any typos, I'm going to go ahead and try to compile 1.c with CS50's library. OK? That's a rare feeling indeed, perhaps for some of you at this point, but that's fine. I know what that's like. Here we go. It's at the blinking prompt. What do I want to add? Let's do something easy, like 3. All right, so 3 plus 2 plus 1 checks out. 6. All right, what about 10? All right, that checks out as well. So we have a working program. The question, though, is can we do this differently? So this is a program that clearly uses an iterative approach to add all the values from 0 up to n. But that problem is really the same as what? Well, if I ask you to add up all the numbers from 0 to n, and I tell you there exists a function called sigma that does it, well, why don't you try to cut corners conceptually and yourself let someone else figure that out and return, for instance, the value I've given you, n, plus what's the sum of all the numbers from n minus 1 to 1? Yeah, you can kind of, right? Well, why bother computing it yourself if you have access to a function that computes it for you, right? So herein lies some recursion, assuming this line of code is in the function called sigma. So let's actually do just this. I'm going to go ahead and go back to this code. So I'm going to use the same framework. I'm going to make a copy of it and call it 2.c. And you have a printout of this today called sigma2.c. In 2.c, I'm going to scroll down, and I'm just going to change my implementation here. So rather than do any of this summation, I'm going to do exactly this. I'm going to return m plus sigma of m minus 1, right? Just let myself deal with it in terms of a smaller problem. So here's that same spirit again of divide and conquer. Why solve the whole problem yourself if you can tear off part of the problem that you can solve and then just repeat that same process? Repeat that same process. But there is a problem with this. Right? What's going to happen if I actually save gcc 2.c lib CS50 and run this thing with the value of 3? That was pretty easy. What just happened? All right, so some of you have seen this problem before. What's it mean in this case? Well, why, first of all, is that broken? So it never stops. So eventually m becomes 0, and it adds m plus sigma of m minus 1, which is now negative 1. Repeat, 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 and it just never actually stops. Well, what's a segmentation fault? Well, recall this slide from last week when we talked briefly about memory management. And we will come back here. Recall that what happens anytime you call a function, that function gets a so-called stack frame in your computer's RAM. Well, how many times is sigma getting called? I mean, a lot, until the point that it overflows the so-called stack. So because we're calling sigma in this buggy implementation again and again and again and again with no intended stopping point, what literally happens is it's as though one of these rectangles, these layers called foo in this picture, just keep getting layered on top, on top, on top, on top. It means the operating system keeps giving you more and more memory for this function's invocation until you finally overlap some other segment, so to speak, of memory. A segmentation fault is essentially when some chunk of memory begins to overlap another chunk of memory, and particularly one that you don't own or that just no longer is within the bounds of the system. You've asked for 2 gigabytes and the system only has 1 gigabyte. So how do we fix this? Well, this is what's called a recursive case, because this line of code does in fact return its number plus itself. That is, it calls itself. How do we fix this? It's actually a really easy fix. Yeah, so let's just stop the problem in its tracks. So if m is less than really 1, the question becomes moot. What do I want to do at that point? Return 0, else I want to go ahead and return not just 0, but instead that. Let's recompile. Let's rerun it with 3 this time. And in fact, we do get back the right answer. So this is child's play, this version of sigma using recursion, but it's representative of an incredibly powerful technique. And later in the semester, when you're implementing your fastest dictionary program in a contest in the course, one of the problems will be for some of you to navigate a tree, which has this sort of repeated structure. And it's in that context of data structures that you'll actually use recursion in a more powerful technique. For now, we'll leave it at that. I'll stick around for questions, and we'll see you in Emerson 105 on Friday.